distributed computing.
You got the massive in there, right?
Yeah.
Indeed. Right, I was promised, or I was told to talk about something in algorithmic foundations for emerging computing technologies, so emerging it shall be. First, I want to thank the Simons Foundation for inviting me here, and also the program organizers, Cliff, Kunal, Kirk, and others. It's been a fantastic workshop and a joy to be here. So I'll be talking about interplanetary and relativistic distributed computing. Before that, a few words about myself. I just joined as a faculty member at Dartmouth, and I lead the distributed computing and verification lab over there, where it's our aspiration to design and deploy simple, fast, scalable, and reliable solutions to fundamental multidisciplinary problems, sort of ranging areas. Everything is of interest, as long as it's interesting, mathematical, and hopefully useful. So to put us in the mood for this talk, I found this wonderful quote, which is from this very ancient text called Atharva Veda, about 1000 BCE, which says, "Time is placed in the cosmos. We observe it from various perspectives." And then a much more concrete quote from Einstein, who says, "The distinction between the past, present, and future is only a stubbornly persistent illusion." Okay, so we're going to be talking about relativity, that is at the intersection of distributed computing and Einsteinian relativity in physics. So motivation: distributed systems are embedded in the physical world, so they're subject to the physical nature of space and time. And Einstein's theory of relativity reimagines space-time with notions like the relativity of simultaneity, time dilation, length contraction, etc. So real systems in the world then are subject to these surprising behaviors of the physical world. We'll be particularly interested in the relativity of simultaneity, so I'll say a couple of words about that phenomenon. So consider two events that occur in our world. Let's say E is the event of lightning striking the Earth somewhere specific. And E prime, maybe it's a solar flare on the sun. Okay, two different events, they occur. The curious truth about such things, according to Einstein, is that you might have two observers, A and B, Alice and Bob, who may disagree on their ordering. That is, which occurs first and which occurs second. Alice may legitimately think and be correct about the fact that E occurs before E prime in her frame of reference, whereas Bob may legitimately think and be correct about the fact that E prime occurs before E, in his frame of reference, right? And it's important here that it's not just when Alice sees the event to occur. For instance, when I see the sun rise, it must have been 8 minutes before or something that the sun actually came over there, that light originated over there. So even if Alice and Bob, they recalculate the real time at which the event occurred, not when they saw it, this is still the case. And this is sort of counterintuitive, and therefore relativity poses a fundamental new challenge to distributed computing because of the way we have to reimagine ourselves, space and time, in contexts where relativistic effects are significant. By the way, at any point in the presentation, feel free to interrupt me. This is a discussion, also a talk, but also a discussion. If anyone has any questions, feel free to ask Kuba.
So can Alice compute how Bob observes the event, or is that also difficult?
Can Alice compute how Bob perceives the event? I guess it depends on what Alice knows about Bob. Right. Okay, that's another can of worms. I suppose an external physicist who models the setup can do various calculations on the system. Whether internal processes, what they're able to understand about each other's perceptions of reality, that's maybe a more complex topic.
Yeah, I think more generally, it's not clear what it means for Alice to think E is before E prime in her framework.
So this is in the sense that Alice is you're thinking of Alice right now as some real observer in this physical world in which there's also a distributed system, perhaps, or in this case, there's no distributed system. There's just things happening in the world, like the lightning strike and the solar flare. And by this I mean the local time of Alice, so to speak. What physicists would call the local time of Alice or the local time of Bob. And the local time of Alice is Alice's true reality of time. And local time of Bob is Bob's true reality of time. And the fact that events that occur in space-time don't coincide in their order in these local times is the point of interest here.
Saying that you're not a physicist. But
That's right.
if you're going to allow Alice to recalculate, I'm going to think it's 8 minutes earlier. I mean, why can't she calculate that it was 16 minutes earlier or something? I mean, it's not clear. And once you allow her to do something other than this is when I saw it and say it happened at some other time, then like it's not.
So I'm not even necessarily saying here, by the way, that Alice, whatever, calculates herself or something, that she does some, I'm not saying she does a computation. I'm simply saying that in the local time of Alice, that is, there's a reference frame associated with Alice. In that reference frame, events that occur in space-time happen at definite times in that local time of Alice. And this happens to be the ordering of those two events in that local time. Right. I don't mean to intend here that Alice is doing computations of when events happen or that there wasn't something blocking her from seeing that event or none of that.
No, but isn't it just immediate? Because if two observers are, let's say, 1 second apart in the speed of light, and the same event happened at the same time, and so one saw like two events happened exactly at their location, so each one saw it 1 second before the other. I mean, A before B, because it happens, they saw it immediately, while the other event they saw it after 1 second.
So I didn't pick up the exact details. The question has to do with some particular example of how observers might be situated and how they might see events. Maybe for now, it's useful to just think that given an observer, there is a local time of that observer. There's a reference frame of that observer. There's a local time that observer experiences. These are just physical truths. I mean, in special relativity, you can calculate when events occur based on these using the Lorentz transform, etc. We're not currently interested in actually calculating them out. We're just making the observation that relativity states that in the local time of A, these events could occur in a certain order, while as in the local time of B, they could occur in a different order.
I think I actually feel, thinking about this, I think it was helpful that you talked about Alice being able to calculate, because I think it's not the fact that they observed something at different times. You're saying they sat down in principle and calculated based on their local time when this could have happened, and they came up with different answers.
Exactly.
So that's the way to think about it. Yeah.
That's one very reasonable way to think about it.
And we're not traveling, Alice and Bob are not traveling the speed of light.
They're not traveling at the speed of light. They're perhaps traveling.
Yeah.
Okay.
But yeah, they're not traveling at the speed of light or something. They could be traveling at normal speeds and perhaps in different directions and so forth. Okay, does relativity actually manifest in distributed systems of interest? The answer is yes, and including a system that we all know and love and are very familiar with and might have gotten us to this location today morning, or at least the first day we were at the workshop. So the global positioning system, the GPS, makes corrections for relativistic effects, at least two corrections, one for kinetic time dilation, the accounting for the difference in speed between the the receiver on Earth, my phone, and the GPS satellite. Another one for gravitational time dilation, because these two parts of the system are experiencing different gravitational potential. There are other emerging distributed systems, like the interplanetary internet, which is basically a connected network of satellites and devices on Earth and Mars, and you can imagine having space stations and telescopes and whatnot, various types of computing equipment in our solar system that can be hooked up together and do interesting computation. And there's increasing interest in space exploration. I don't know if this Mars One project currently has any funding or not, but they were interested in setting up a colony on Mars. Okay, SpaceX and Blue Origin and various companies in industry are interested in the general realm of space exploration. I mean, going to the moon, going to Mars, possibly sending people up, this type of thing. So it's very interesting at this time to be studying how the computational framework behind all of this distributed computing in space works and what's interesting about it. So I will say some things in greater detail later, but just so that we're approximately on the same plane of thinking, space-time and causality. In relativity, events occur in space-time. We'll let that blackboard bold E represent the set of space-time events. Events are partially ordered by a causal order. So we saw that they're not totally ordered by the local times in the relativity of simultaneity example, but events are in general partially ordered such that if E was a cause of E prime, then E precedes E prime in this order. We say that E, that curly less than sign, precedes sign E prime if a hypothetical pulse of light could originate at E and reach E prime. Any given reference frame, for instance, the reference frames of Alice and Bob in the previous slide, turn this partially ordered set of events into a totally ordered total order, here given by this less than R. This thing is called a chronology. Yes, Ratish?
Model from the future going back in time?
No, I'm modeling this. I'm modeling this. Nothing about time travel going on here. So the question was about time travel, I guess, in general. Nothing time travel-y happening, at least in these slides. I don't know if there's time travel in the universe or not. Another interesting point to remember is that point-like objects, so we're going to be thinking of processors, for instance, as point-like objects. They trace out curves called world lines in this space-time space. And the events on a world line are actually totally ordered by the precedence relation, which otherwise only partially orders events. So two events that occur at the same processor will have a definite order. Okay, a roadmap for the talk. First, I'll lay out some background about things that many of us think about all the time, distributed computing, asynchronous algorithms. I'll say a thing or two about shared objects, and then we'll put a little bit of focus on linearizability, this famous correctness condition. And we'll look at why linearizability, the definition, may be a bit ill-posed in this distributed system case. We'll think about resolutions to that. And then the main contributions in this talk are going to be, well, how do we think about distributed systems in relativistic physics? Well, I'll take the physics and I'll reduce it to some physical postulates, which is all we're going to have to need to worry about for the case of this talk. There'll be both classical postulates and relativistic postulates, and it's just a few of each that we'll have. And then we'll model distributed algorithms and executions in both the classical and relativistic space in some unified way, thereby allowing us to establish some strong links between relativistic and classical computing. And then I'll make, finally, a note on some curious behavior of relativistic algorithms that can occur even though there are these nice, strong positive results that will show up in the point before that. And I'll end with some final remarks. Is that a hand, Eula? No. Fantastic. OK. So distributed computing, we're interested in distributed systems. What are distributed systems? Well, they're systems that have two or more processes and some non-trivial communication. Distributed algorithms, we generally think of them as coming in two flavors, synchronous and asynchronous. I'll be focusing on asynchronous algorithms, those without clocks. A challenge with asynchronous algorithm is that there are several possible executions due to non-determinism in the relative processing speeds and message delivery times.
Would it make sense to consider synchrony at the space?
So this is actually, you will see on my last slide, this I believe is an interesting open problem. How to incorporate clocks into this framework to do interesting things. I mean, certainly the GPS is an example of a system which uses clocks to do something very interesting in a distributed computing setting. The model we'll see right now is going to be an asynchronous one, and therefore that will not fit directly into the model. So some type of expansion with clocks needs to be done in order to properly account for these types of behaviors. But I think this is an important open direction. Okay, and then we say an algorithm satisfies a property only if all possible executions, a property will be something of an execution of an algorithm. And we'll say the algorithm satisfies the property if all possible executions of the algorithm satisfy that property. Take linearizability as an example for those who are already familiar. Shared objects are an important class of distributed algorithms. These are objects which are implemented across and accessible to the various processes of the distributed system. Examples include large key value stores, concurrent set union objects, queues, stacks, other common data objects. A central question several decades ago was, what does it mean for a shared object implementation to be correct? And I guess the gold standard for that is linearizability. Let's just recall what the linearizability definition says. In linearizability, it says, well, if I have some shared object, it can create, and I run some algorithm on it, it can create a history, which is a set of events which are invocation or response events here, those diamonds. And they're totally ordered over time, right? And then I say that I like this execution. It satisfies linearizability if these operations, which actually take place over intervals of times, appear to take place instantaneously at linearization points, which are sometime inside those intervals. Of course, immediately, something interesting happens given our previous discussion of relativity of simultaneity. The linearizability definition of here is assuming absolute time, this axis over here, and therefore it's slightly ill-defined in the relativistic setting, right? We need something new. Okay, this problem was identified by Seth Gilbert and Wojciech Golub in a 2014 paper in which they propose a few different possible definitions of what linearizability could mean in the relativistic setting.
So, Siddhartha, the problem is that you cannot define the execution interval. What is the actual problem, right? Because there are...
Say again, Yula?
The problem is that you cannot easily define the execution interval in this setting.
That's right. You can't properly define the relative orderings of these events.
The relative ordering.
The relative orderings of these events.
I see.
The invocations and responses and so forth. Once you take away the absolute time and you go into the partially ordered setting. Question.
Can you go back? So there, an individual, in our setting, are we thinking of pi 1, I don't know, happening at the same space or something like that? Is that something?
So pi 1 here, okay, so here in classic linearizability, Hurley-Wing, you don't care so much about space. I mean, there's absolute
Correct.
time, so things are happening in time.
Yeah.
But yes, when you go to the relativistic setting, pi 1 will be a point-like object in space-time. So it will trace out a world line. So I'm not assuming that it's sitting around. It might be moving, like a satellite would be moving or something.
But there is a notion of
But yeah, I'm thinking of it as a physical entity, which is a point-like entity, which is whatever, zipping around in a world line.
A second question. I'm not that familiar with the literature, but there is also a lot of work around sequential consistency, weak consistency, which are weaker notions than linearizability, I believe, which seem to be similar to what...
Which have some relevance to this area, yes, indeed. So the question was about other forms of consistency, right? Other forms of shared shared object correctness that you might consider like sequential consistency or this other type of stuff. And those correctness criteria, they're not composable, which makes them a bit hard to work with. So the objective would be to come up with something which is truly sort of like linearizability insofar as possible. I mean, there's a reason why we know and love linearizability in the classical context. Is there something like that in the relativistic context that we can latch onto and make our new gold standard? But indeed, it's interesting to think about these. In fact, there's some thinking about these, and they're not composable and so forth. So they have some undesirable properties. Perhaps they also have some desirable properties, but I won't go into that more over here. So in the relativistic case, a history is once again going to be a set of events, right? There's still invocations and responses that the system is generating. It's just that they're now partially ordered by the partial order of space-time. And so what could you define relativistic linearizability as? Well, Gilbert and Golub, they give three possible definitions called R1, R2, and R3. R1 says, well, look at what happened. And in any reference frame, you'll get some total order, right? The partial order will turn into a total order. Okay, there might be some total orders which don't necessarily correspond to reference frames, but they say, okay, let's leave that out for now. Let's think mathematically. If there's some total ordering of this partially ordered history, which appears linearizable, then R1 says, I like that. That's R1 linearizable. Okay? R2 says, well, natural choice. Okay, if every total ordering of that partially ordered history is linearizable, then R2 likes it, and okay, that's such a thing as R2 linearizable. And then you might wonder, well, these various total orderings, once I do the total ordering and I find a linearization, will that agree across the total orderings? And it may not. So R3 says every total ordering of the history is linearizable, and all the total orders agree on at least one linearization. They prove an interesting theorem that R3 might seem like the coolest one over here because it's guaranteeing you the most. Turns out R3 is not composable, R1 is not composable, but R2 alone is composable in these definitions at least.
You just skip one sentence what composable means.
Oh, yes. So composable, which is also sometimes, basically what I mean by this is if I have a Q object, which is R1 linearizable, and I have a stack object, which is R1 linearizable, can I think of the system of the Q and the stack as also being R1 linearizable? This is the question. And in the case of R1, this does not hold. I can have a Q that's R1 linearizable and a stack that's R1 linearizable, but the system of the two objects together is not R1 linearizable. Same, it turns out, is true of R3, but in the case of R2, if both the Q and stack are R2 linearizable, then the system composed of the two is R2 linearizable. And this is one important property of linearizability in the classical sense, which would carry over if you use R2 linearizability in the relativistic sense.
R3 seems stronger than linearizability, is it not?
So R3, if you take classical executions, that is, if your events were already totally ordered, then R3 and R2 are entirely identical definitions, right? Because there's only one total order, so in fact they're all identical in that case, right? Because things are already total ordered, so if there's some, then everyone is also. So yeah, it's hard to compare these directly to linearizability in that way because they all reduce to linearizability when the partial order becomes a total order in the a priori part. Okay, so they showed this interesting fact that this R2 definition, which sort of looks kind of nice, is a composable definition of correctness, but there's an open problem that's left there, which is the discovery of, in fact, any relativistically linearizable algorithms, right? Nothing was said about algorithms. Okay, in this talk, we'll use actually something which is slightly a variant of this as our definition of relativistic linearizability. It's similar to R2, but defined slightly differently. So instead of talking about total orders, we'll directly talk about reference frames. And our definition of relativistic linearizability will be inspired by R2, and it'll read, we say a partially ordered history is relativistically linearizable if it is linearizable in every chronology, i.e. in every reference frame. That is, for all reference frames, the reference frame ordered event history is linearizable. And then we have a theorem, which is that relativistic linearizability is composable, as defined here. Kirk.
So is it like is it just a restatement of R2, or is it there's like some subtle differences that you're?
So there's a subtle difference which we don't need to dwell on a lot over here. The question comes down to, are there total orderings of the partial order which don't correspond to reference frames? And it seems the answer to this question is that in general relativity, R2 and this are identical, but in special relativity, they're different. We can ignore that for the rest of the talk.
But what's the formal definition of the chronology of every?
Sorry, Eula, say that again.
What's the formal definition of the chronology of every reference frame?
So chronology is just the local time of that reference frame. And for our purposes, once again, let's ignore these subtle differences. I only put this up to say that this is what the object is. Basically, this chronology is going to totally order that partial order. And this will suffice for everything we're going to say here.
Do you actually use it? The difference between this and R2 later on?
No, we don't.
Okay.
We're not going to use that in this talk. I just think it's nicer physically to define it this way.
But does this mean that your results
That's right, they'll also apply for R2. So the results will apply to R2 and for this definition. For all intents and purposes, and so far as this talk is concerned, we can ignore any differences between the two. Okay, so what are our contributions? First, we designed a unified model of classical and relativistic and something called computational distributed computing. I'll say what that is in a little bit. In both the message passing and shared memory models of computation. Then we show an equivalence theorem which is very strong. We say that an algorithm, so previous state of affairs, we don't know any relativistically linearizable algorithms. Now we know a ton of them, right? Because we proved that any algorithm which is classically linearizable will be relativistically linearizable. And also vice versa. And also vice versa. This is for asynchronous algorithms, right? We're thinking about asynchronous algorithms. In fact, we prove something that's even stronger than this. We prove what call a central theorem. Let A be an algorithm, P be any property. Now, not necessarily linearizability, that's just our example, but let P be any property. Then the following statements are equivalent. That A satisfies P in every classical execution. That is, A satisfies P. And that A satisfies P in every reference frame of every relativistic execution. Right? So this is the natural widening of that linearizable over there to an arbitrary property P. So the central theorem is a very strong positive result if what you're interested in is that your system behaves well according to every single observer, even though, as we'll see later in the talk, those observers may still disagree on why they think the property holds. I'll pause here. Are there any questions before we're going to now get into the more technical part of the talk, which will talk about physical modeling, what distributed algorithms in these two settings look like, and how you prove this theorem. I won't go through the details of the proof, but hopefully I'll say enough that you're inspired to believe in the theorem. Yes, I will take all of the questions.
When you say the equivalence theorem there, is the linearizability the same on both cases? Is it linearized the same way in both classical
So once again, similar to the discussion we were having about R2, all we're saying over here is that each of the observers is happy with, like he looks at that whatever transpired and says, yes, the property holds. So I say this property holds, Kirk says this property holds. We might disagree on why we think the property holds, right? And that's the curiosity we'll get to at the end.
So, I mean, it sounds like, I wonder what exactly this model is capturing, because it's the way I read it means, well, after all, it looks like we can design the algorithms the usual way and they would still work in this relativistic setting. Is that the proper reading of this?
So that is one. So the Kuba's question is about what is the proper way, so to speak, to read this theorem. Does it essentially say that I can sort of not worry about the relativistic issues and everything will be fine? And the answer is yes or no, depending on what you care about. Right? It all comes down to what you care about. If you're happy with the guarantee that this gives, right, that I've designed a distributed algorithm that's running in this relativistic physics, I'm happy to think that it satisfies my property P if individual observers think that it satisfies P, even if they disagree on why it satisfies P. If that makes you happy, then yes, you can ignore the relativistic in the asynchronous case too. Okay, then you can ignore all of this and you can use this powerful theorem. You can design based on just classical thinking. If that doesn't make you happy, you're dissatisfied that observers might disagree on orders and so forth, then you'll have to do something more. This theorem won't come to the rescue. Yula? I think so. The question was about where is the asynchrony used in the proof of the theorem. We'll see what the idea behind the proof is, and then maybe if there's a lurking question still. And I think part of the question is actually pinpointing in a beautiful way. If we can figure that out, then maybe we can actually say more, or maybe there are other things we ought to say, and so forth. But that's a very good question, I think. But we'll see at least somehow what the big ideas are. Fantastic. Okay. So what's the modeling? How do we model these systems? So important to understand at the top, distributed systems. So we talk about systems, algorithms, executions, computing, etc. Distributed systems, that is the processors and etc., are embedded in the physical world, right? So they can be modeled by physical postulates. Distributed algorithms are purely mathematical, right? There's nothing physical about the algorithm. The physical part is in the system. And we model them as state machines the classical way. The notion of an execution is the glue between the physical world and the mathematical algorithm. So when we get to the definition of executions, that's when everything will come together in an interesting way. And these will be modeled as ordered sets of steps, kind of like the ordered histories that we saw before, partially ordered or totally ordered, depending on the physics. So how do we model the classical physics? We'll be interested actually only in two physical postulates, which we'll call CP1 and CP2, classical postulate 1, classical postulate 2. CP1 says events of interest occur at distinct times, right? In the classical physics, distinct times, and they're totally ordered by the chronological total order of time. Number two, we're interested in message transmissions in a distributed system. Message transmissions can be arbitrarily fast classically, but are always oriented forward in time. I can't send a message to the past. Okay, so maybe I say something about Ratish's question. I assume we can't send messages to the past, only to the future, classically. Okay, this we all love and are familiar with. Relativistic postulates. What are the corresponding ideas here? RP1, events occur at distinct space-time events, partially ordered by the relativistic causal order, given by this curly precedent sign. And each reference frame R has a refining total chronological order. This is all stuff we already talked about. RP2, processors are point-like bodies that trace out world lines. This, of course, means that events at a processor are totally ordered because events at world lines are totally ordered. And finally, RP3 about messages. This is where our friend speed of light comes in. Message transmissions can travel up to the speed of light. They're physical transmissions, but no faster. Thus, message send events precede message reception events. That's all we're going to need to know about the physics. Okay, nothing more.
That's all we care about, just the last part.
For RP3, yes, these postulates are the only things that I'm going to use in physics.
No, but for RP3, the only thing as far as you're caring about is message send is before message receive, or you're actually going to use something about speed of light, or?
Am I going to use something about the speed of light? This is all I care about. This is all I care about. I'm also going to assume they have at most one semantics. That is, a message will not be delivered multiple times. So what's a distributed algorithm? That was the physics. What's a distributed algorithm? This is classical. This is like the modeling that you would see. A distributed algorithm is simply an algorithm for each processor. An algorithm is a state machine, which is defined by a transition function. Any processor is in some given state. If some event transpires over there, it moves to some next state. That is, it runs in steps. Sigma is the previous state. Event E occurs. Sigma prime, the new state, ensues. Events include message send, message reception, and local steps. So those are the things that E could be. Note, this is all physics independent. What glues the physical postulates of the distributed system to the mathematical distributed algorithm notion? It's the principles of physical execution, of which we'll have 3, which will be applicable to both systems. Phi 1 says processors are point-like bodies that start in an initial state. Okay, so processors start in an initial state, and execution consists of a set of steps of a distributed algorithm. Note that these steps are local steps. Phi 2 says that consecutive steps at a given processor are consecutively permissible according to the algorithm. That is, if I have a step at a processor sigma E sigma prime, and the next step is sigma hat E hat sigma hat prime, then that means that since this was the next step, this sigma hat should be the same thing as the sigma prime. Just as you would expect. Phi 3, maybe this is what you were asking about. Message transmissions are physical transmissions with at most one semantics. This is going to glue to that RP3. And these are the physical execution postulates. With these, you get physical executions, right? If I define an algorithm in the system, I immediately get all possible physical executions. What is a physical execution? Well, a classical physical execution is just a set of steps and a temporal map that says at what time did each of these steps occur. A relativistic physical execution is just, once again, a set of steps and a space-time map, epsilon. At what space-time event did these steps occur? That's all a physical execution is. We can extract from these preserve explicit information about time and space-time events. Yes, Cliff?
Some notion of data or memory, like or a tape, a classical machine has a tape. Like, it didn't seem to.
So this is all caught in the notion of the state. The state, by the way, as is often done in distributed systems, that doesn't necessarily come from a small set. Right, that's sigma. Those sigmas that you see, those don't necessarily come from a small set. I'm talking here about the message passing. If you have a shared memory thing, basically, if you have a shared object, you'll consider that basically something like a processor. And that thing will have all of its state. If I want to do an operation, I'll send it the operation. It'll send back a return value after updating itself. So you can also think of memory exactly the same way. It's just a bunch of memory modules which are hanging out in the same place or in different places. So in these physical executions, unlike we're commonly used to, we're keeping explicit information about the time and space-time. Okay, generally we don't care about this, so we can just extract out just the orderings of the steps. This is what we normally get to for classical executions, that there are a set of steps and total ordering between them. And similarly, we can extract out of the relativistic physical executions, just relativistic executions. Physical should be removed from there, which is just a set of steps and the precedence order, which is partial. And a property P is a predicate on classical executions like we're used to, easy linearizability. Okay. That's all for the modeling. With this model, we'll achieve the results. How do we do it? How do we relate classical and relativistic distributed computing? The key idea is going to be this idea, which I briefly mentioned before, computational executions, which are going to be purely mathematical. Key ingredient, computational execution. It's going to be purely mathematical, completely physics independent. And it's going to be based on Lamport's happens before relation from that very famous CACM paper in 1985 about time clocks and ordering of events in distributed systems. What is a computational execution? Well, it's an execution of an algorithm, so we should say something about the algorithm. Okay, it's going to be, once again, a set of steps. These are local steps with some partial ordering given by this triangle less than sign. And it's going to satisfy 3 axioms, which are going to define right now. A1 says that S is a set of algorithmic steps, and that the partial order is a transitive closure of the relations obtained by A2 and A3. A2 says that the steps at a given process are totally ordered by the precedence relation and consecutively permissible, as we saw before. A3 says that messages are oriented forward in time. Okay, they all start to look somewhat similar. What exactly is going on here? Think of this triangle less than as capturing just the relations between the computational steps. In relativity, remember, the partial order is capturing things about hypothetical pulses of light and what might have happened, et cetera, with those light. Here, we're only capturing things which are computational in nature, precedences which are computational in nature. The intuition then should be that all of these precedences continue to exist both in the relativistic physics and in classical executions. That this is like an internal skeleton that's occurring in both of these physics. That's the intuition. Now we can state the central theorem. So we say let A be an algorithm and P be a property, then the following 3 statements are actually equivalent. And the third statement is what's going to give us the kicker to complete the if and only if statement that I showed in the original slide. The first one says that A satisfies P in every classical execution. This is A satisfying P classically. A is linearizable, for instance. The second one says that A satisfies P in every reference frame of every relativistic execution. This is, when you read their linearizability, this is A is relativistically linearizable. The third one says that, in fact, A satisfies P in every total ordering of every computational execution. Remember, the computational execution were the least ordered of the executions. So even if you take the least ordered thing and you take any total ordering of it, P will be satisfied. How do we prove this theorem? And if we prove this theorem, of course, we get the equivalence theorem about linearizabilities for free, with also some notion of computational linearizability. How do you prove that theorem, though, the central theorem? Well, the ideas will be the following 3 lemmas. We'll show that every relativistic execution refines some computational execution. That is, a relativistic execution is a computational execution just with extra partial order information added in. Then we'll say that every total ordering of a computational execution, so the least ordered guy, make that guy totally ordered in any way you want, it's going to be a classical execution. And in fact, every classical execution can be obtained in this way. Every classical execution is going to be a total ordering of some computational execution. So there's a tight relation between these 2 notions. And finally, we'll show a lemma that says every classical execution is in fact a relativistic execution. That is, you can get in the relativistic physics these totally ordered executions. The idea here for proof is that you bring the processors together so that they're all following the same world line. You can get these executions. Okay, I won't go into the details of these proofs. I hope the intuition is somewhat clear. The details in the paper, basically the proofs make careful use of the physical postulates CP1, 2, and RP1, 2, 3, of the physical notion of execution Phi1 through 3, and the axioms of the computational executions A1, 2, 3. So you glue these together in the right way, and you get these lemmas. From these lemmas, the central theorem ensues. And you get the central theorem. And then the equivalence theorem is just substituting in the property as linearizability. Now, a note on curious behavior. Okay, so this is a strong positive result, right? Like, strong positive result. But does this mean that nothing interesting is happening in the relativistic space, at least for asynchronous algorithms? No, interesting things continue to occur, as we will see in this note on curious behavior. which is going to be about a phenomenon which I'll call chronological invertibility of operations. So firstly, let me define what I mean by this. Take some operations op1 and op2. We say that they're chronologically invertible if there are observers, Alice and Bob, such that Alice sees op1 before op2 fully, like op1 finishes and op2 starts later. And for Bob, op2 finishes and then op1 starts later. Okay, then we say op1 and op2 are chronologically invertible. So observers necessarily disagree, like Alice and Bob have to disagree on the linearization order of chronologically invertible operations. Proof by picture. So then there's a question, can this really occur? Can chronological inversions occur? And can they occur at solar system scale? For instance, in the interplanetary internet of things near Earth and Mars and so forth. Okay, the answer will be yes. And let's see this by doing this thought experiment. I won't work out all of the mathematics on the slide, but we'll see why essentially what's involved in having this chronological invertibility occur. So here's a nice thought experiment. We have two processors here, pi1 and pi2. They're far apart at a distance of, okay, and then we have three observers here, an alien who's sitting in the middle of them. Imagine the alien as being sort of static. I'll describe things in terms of how the alien perceives them initially. And then we have this man who's flying in this direction and this woman who's flying in this direction via spaceship. And here's what occurs. The man and woman travel with constant velocities, all of this with respect to the alien, right, of v and negative v. Each of the processors is a distance d away. And it so happens that the man and the woman coincidentally go past the alien at some event, right? Okay. On the other hand, these pi1 and pi2 are part of some system that's executing a shared memory object. It's going to be a shared concurrent union find object. And the beauty of the concurrent union find object is that you can have operations which are on one tree, one connected part of that object, which rests maybe entirely in pi1, while there could be some other part of the forest, some tree that's entirely in pi2, which means that if pi1 does an operation which happens to only need nodes that are in the pi1 side of the part, it doesn't need to send any messages. Same with pi2, right? If pi2 does some operation on some nodes which are all over here, it might not need to send any messages. Consider such operations. So let op1 and op2 be such operations on shared memory union find. And from the alien's perspective, let's say that both operations run over a time, and they'll run over a time interval from 0 to t. Okay, you could say t1 and t2, and okay, you'll just get something more complex. But main point will be observable here. So this is the thought experiment. Thought experiment is clear? Okay. You can derive, here I'm thinking of a situation in special relativity, no gravity. You can derive using the Lorentz transform, etc. This following equation for when chronological invertibility between these two operations, op1 and op2, will occur. And okay, it says 2vd is greater than c square. C square is huge, times t. Okay, basically, c square is some huge quantity that this thing is going to need to beat in terms of t. And you can read this abstractly as saying that the speed of these guys times the distance should be much, much larger than the computation time, right? Because of that c square that needs to be overcome for this relativistic effect to really kick in. So if this is going to happen, it's because distances are huge and computational times are very small. And we're going to take speeds which are actually very natural speeds, escape velocity of the Earth or something as the speed. Okay, so what happens when you plug in speed of light for c? Okay, escape velocity of Earth for the spacecrafts. This is like a normal speed at which you might think spacecrafts will be going. And distance from Earth to Mars, which is huge as the distance. Because computation is so fast, running at gigahertz or 5 gigahertz or something, you can actually run operations which take something like 10 to the 7 clock cycles, and they will actually invert in Earth to Mars scale distributed systems. Okay, and then you can do this with, since the concurrent union find object, it has logarithmic height trees, and as Bob told us in his talk, he did some derivations. Okay, it's actually very, very fast. You can actually do computations on huge graph instances that will finish in this number of clock cycles using normal machines, normal speeds, and normal distance between these in interplanetary scale. So chronological invertibility can occur, and relativistic distributed systems are here. Okay, conclusion, chronological inversions can occur at interplanetary scale. Processes may necessarily disagree on linearization order, even though they agree on linearizability, according to the central theorem. Okay, so we did the model, central theorem, equivalence theorem, and we showed this chronological invertibility truth. Summary of the talk. Relativistic distributed computing is a new fundamental model of distributed computation. The central theorem and equivalence theorem are strong positive results that show an elegant relationship between computational and physical notions of causality, strong property preservation in relativistic distributed computing. However, chronological invertibility is nevertheless unavoidable at interplanetary scale. Looking into the future, current directions, what am I working on now in these directions? A few different things, all which I find very fascinating. Okay, linearization orders you can't agree on, but there are two common views on linearizability. One is the one which I sort of presented, right? I presented the points. I didn't talk about the partial orders when I defined linearizability. So how about the points? Can we agree? Can we have absolute agreement on linearization points? The answer is sometimes yes. Okay, write up forthcoming. I call this notion atomizability. Operations appear to take place atomically. And you can have absolute agreement on the space-time events at which all processors observe this operation to take place instantaneously at. Okay, this is atomizability, fun stuff. So maybe you can retrieve some of those aspects that we were trying to get out of that R3 definition that Gilbert and Golub were defining, just in this very different manner. I talked about properties here, also investigating hyperproperties like strong linearizability and how do you do this, etc. Relativistic epistemology. So hopefully have something forthcoming here also about the logic of knowledge in relativistic computing. Can you know or can you not know that you're in a relativistic system versus a classical system? And you can do some reasoning about this, and that's very exciting.
The second is kind of related to the first, right? So if you have a positive answer for the first, then there is hope for the second.
Then there is hope for a positive answer for a second, yes. And I believe that there is a positive answer for the second. In fact, the union find object, concurrent union find object, is a strongly linearizable object, at least for the union and the find. And you can show atomizability for it is the idea, right? And then you can show, in fact, a strong atomizability for it. And yes, but yes, indeed. Without this, it would be a bit hard to reason about what's going on over there. But yes, indeed. So the question was about relationships between hyperproperties and strong linearizability, in particular, and atomizability. And I believe that there's interesting relationship. Okay, this is relativistic epistemology. Okay, I also have an ongoing collaboration with some friends on quantum relativistic computation in quantum field theory, QFT, this type of interesting ideas of how causality and quantum and relativity and computing and stuff interact. Open question. Everything I talked about, I didn't talk about clocks. GPS uses clocks. I mean, the whole GPS computation is entirely about those atomic clocks and passing around those values, etc. There's clearly some barrier. The central theorem is saying like things are pretty much honky-dory in this asynchronous setting when you go to relativity. But in GPS, we're having to do explicit corrections for relativity. So there must be some interesting barrier here, right? You move in from these two, you get somewhere. What is that? And Yula, you were asking at the beginning. Yeah, I think this is an important, interesting, open question. To end it all, space exploration is a fundamental quest of mankind. Distributed computing is a key tool in this exploration, and I'm eager to collaborate on exciting problems that arise with a goal to develop a comprehensive understanding of relativistic distributed computing systems. that's all I have for you today. Happy to take any questions.
Anybody have any questions about special or general relativity for Siddhartha?
You'll see.
Where do you publish such results?
So this is all based off of a paper which I published at PodC 2025, the previous PodC. But yeah, hopefully more places.
So there are people that understand can evaluate it in that sense.
So for instance, the authors Gilbert and Golub were PC members at that PodC, so I thought that was good. Gilbert and Golub of that R1, R2, R3 paper were on the PC, so I figured it was a good place to.
Now you can see that PodC is a very modern conference.
That's right. PodC is a very modern conference. And in case you want to have a workshop at PodC, I'm the workshop chair of PodC. So all of you, I'm sure, could give wonderful workshops and tutorials. But yes, it was at PodC 25.
Won't ask if you implemented your algorithm.
No, but I'm excited. Okay, so not at interplanetary scale at least. But I can say the following. I was very fortunate. Okay, so how did I? There were a few things that inspired me to do this work. I have to thank my guru Robert Tarjan for inviting me to Heidelberg in my first year of grad school, where Vint Cerf gave a talk on the interplanetary internet. My thoughts on this were like 5 years later, but once I started thinking about this, my mind immediately went to that talk and that there was this interplanetary internet system. So while I was at Google until earlier this year, I talked to Vint, and he got quite excited about this, and he, just a couple weeks ago, I gave a keynote at the Interplanetary Networking SIG, which is a part of the Internet Society. And we'll see if there are folks who are able to maybe implement some of this and maybe do experiments to see the chronological inversions occur or something. I mean, I think it would be very exciting to do all of that, but yeah, not yet. Emerging, it is emerging technology.
You mentioned this last piece of work related to quantum field theories. Are there some effects that happen like this at a smaller scale that some of this implies to?
I see. So this last portion, I guess the investigation has still been about, for example, the example of quantum computers off in space, as opposed to something teeny tiny occurring. Things could occur at a teeny tiny scale. I haven't worked out any calculations myself. I don't know if others have. Rizal was also asking a question about what can happen at teeny tiny scale before the talk. Yeah, it's possible that interesting things can occur. I haven't worked out any of that mathematics, but yeah, I guess we've been thinking about sort of quantum computers in space, and apparently, I read over the summer. Okay, I don't have further verification of this beyond seeing something in the ACM news. Apparently, some people in Europe sent up some quantum device into space, some quantum computer into space. I mean, I don't know exactly where the technology is there, so about what that thing does or anything, but yeah, maybe we have a future of interest. I guess you don't need to super cool things if you send it to space.
All right, let's thank Siddhartha again. So thank you for everybody showing up. I hope you enjoy your lunch. We're done.
Thank you to the organizers.